We will now discuss an important topic in LP spaces, namely that of duality. So the LP spaces are all Banach spaces. Therefore, whenever you have a Banach space, it is interesting to know what is the dual space. The dual space is the space of all continuous linear functionals on the Banach space that itself forms another Banach space. So we would like to often compute what is that dual space, and the study of the dual space often gives us a lot of information about the original space itself, and therefore it's important to know what is a dual space, and that is what we are going to do now for the LP spaces. So we have XS mu measure space, and you have 1 less than equal to p less than equal to infinity, and then p dash is the conjugate exponent. That means if p equals 1, then p dash equals infinity, and vice versa, and 1 by p plus 1 by p dash equal to 1 in the case 1 less than p less than infinity. So this is what the conjugate exponent is there. So let us take G in LP dash mu, and if f is in LP of mu, then we define Tg of f equals integral over x fg d mu, and this is well defined because of the Helder inequality. So Helder implies mod Tg of f is less than equal to norm fp norm g p dash, and so this implies that Tg is a continuous linear functional on LP mu, and norm of Tg is less than equal to norm g LP dash. So our aim is to show for sigma finite spaces. So for sigma finite spaces and 1 less than equal to p strictly less than infinity, we wish to show every continuous linear functional on LP mu occurs in this way, and we have equality in star. So not only, so in other words, this G going to Tg, that is G going to Tg, is an isometric isomorphism. It's a 1-1 on 2 continuous map, and therefore it is isomorphism by the open mapping theorem, and it's an isometric isomorphism because the norm is preserved. So between LP dash mu and LP mu dash, which is the dual space of the thing. Okay. Okay, so now we will prove this result. So proposition. First we will dispose of the uniqueness. So XS mu sigma finite measure space 1 less than equal to p less than infinity, Gi I equals 1 2 in LP dash mu such that Tg1 equal to Tg2. Then G1 equal to G2 almost everywhere. So in other words, the map G, that is G going to Tg, is injective. Okay, so this 1-1 map. So let us prove this theorem. Okay, so proof: f is in LP mu, then integral over x f into G1 minus G2 d mu equal to 0. That is what we mean by Tg1 equals Tg2. So E contained in X, set of finite measure. Because it's finite measure, then chi E belongs to LP of mu. Therefore, integral over E G1 minus G2 d mu equal to 0. Now, if E is in S, because of sigma finiteness, E equals union EI, I equals 1 to infinity, EI is disjoint, and mu of EI finite for all I. Then this implies that integral over E G1 minus G2 d mu equal to 0, because you can apply it for each EI and then add them all up, and therefore this implies that G1 equal to G2 almost everywhere. So you know how to do this. Take the set which is strictly positive, show that it's of measure 0. G1 minus G2 strictly negative, show that it's equal to 0, measure 0, and therefore you have G1 equal to G2 almost everywhere. We have done this before, and therefore you can. So this proves the uniqueness. Okay. So now you have that G going to Tg from LP dash mu to LP mu dash, the dual space is injective and continuous. To show it is surjective and anisometric. Okay, so we will first prove it in a finite measure space, then we will look at it in a general case, sigma finite. Before that, anyway, we need a very interesting lemma. This is a nice lemma. So this shows XS mu measure space. G x to R measurable. Assume for every mu E positive, you have that modulus 1 by mu E integral over E f d mu G d mu, sorry, is less than or equal to K. Then mod G is less than or equal to K almost everywhere. Okay, so if mod G is less than or equal to K almost everywhere, then this is obvious. Now we are showing the converse, namely if you have it for every set with positive measure, if the average, this is called the average over the set E, namely you integrate and divide by the measure, so that's called the average of G over the measure. If the average is less than or equal to K, then mod G is also less than or equal to K almost everywhere. The average of course should be for every set. Okay, so proof. So U equals set of all T in R such that mod T is greater than K. So this is an open set, and let A minus R, A plus R, sorry, you define E to be, so A minus R, A plus R, let be contained in U, be an interval, finite interval contained in U. Let E equal set of all x in X such that Gx belongs to A minus R, A plus R. Okay. Now, if mu E is positive, then you have AE of G equals 1 by mu E set integral G d mu over E. Then mod AE of G minus A equals 1 by mu E of integral over E G minus A d mu. A is a constant, so if I integrate over E, I will just get mu of E times A divided by mu of E, it will give you A again. So this I can write like this. But G minus A, because we are in E, G minus A is less than or equal to R, so this is less than or equal to 1 by mu E integral over E mod G minus A d mu, but this is less than or equal to less than R, okay, and therefore you have that this is equal to less than or equal, strictly less than R. Okay, so this means that AE of G also belongs to A minus R, A plus R. Okay, and that is less than contained in U, and this implies that mod of AE of G is greater than or equal to K, which is a contradiction because you are told that for every set of positive measure the A average is less than or equal to K. So this implies that mu E equal to 0. Now set of all x in X such that Gx is greater than K can be covered by a countable number of sets of the form E. Since U is the countable union of intervals. So each set of this form is of measure 0, and therefore this implies that mod G greater than K, the measure of this equal to 0, that is G mod G is less than or equal to K almost everywhere. So that proves this. Okay, so now let us theorem. Let XS mu be a finite measure space. We will first prove it in the finite case and then move on to the sigma finite case. 1 less than or equal to P less than infinity. T belong to LP mu dash, that means a continuous linear functional. Then there exists a unique G in LP dash mu such that T equals TG and norm T equals norm G P dash. So we are proving the surjectivity and the isometry in this case. Okay, so proof step 1. Now mu is finite measure, therefore chi of E belongs to LP of mu for all E in S, and therefore define lambda of E equals T of chi of E. Then of course lambda of the empty set is chi of the empty set is the identically 0 function, so T of 0 which is equal to 0. Now if A and B are disjoint, when chi of A union B is chi of A plus chi of B. So this implies that lambda is finitely additive. Since T is linear. Now let E be the union EI, EI in S, EI is disjoint. Then we do the usual thing, Fk equals union I equals 1 to K of EI, then Fk increases to E. Then mu of E minus Fk is equal to, since you are in a finite measure space, you are allowed to subtract. Let me write this. So mu E equals sigma I equals 1 to infinity mu of EI, and that is finite, and mu of E minus Fk is mu E minus mu of Fk, and that's equal to sigma I equals K plus 1 to infinity mu of EI. And this tends to 0 as K tends to infinity, because you have this the tail of a convergent series, and therefore this has to go to 0. Then therefore this implies that norm of chi E minus chi of Fk in LP, this is nothing but mu of E minus Fk, because that's where it is 1, everywhere else it is 0, power 1 by P. Okay, and therefore this goes to 0. So chi E converges, chi of Fk converges to chi of E in LP mu. Therefore T of chi of E chi of Fk converges to T of chi of E, which is equal to lambda E. But this is a finite disjoint union, so this is equal to I equals 1 to K lambda of chi of EI, lambda of EI, and therefore you have lambda is countably additive. Implies lambda is a signed measure. Now if mu E equal to 0, this implies that chi E equal to 0 almost everywhere, that is chi E equal to 0 in LP mu, and therefore this implies the lambda of E, which is T of mu E, T of chi E equal to 0. This implies that lambda is absolutely continuous with respect to mu, because no. So by the Radon-Nikodym theorem, there exists a G which is greater than or equal to 0, such that lambda e equal to integral g d mu over e for all e in S. So, by linearity of t, if phi is any simple function, we have t of phi equals integral phi d mu, phi g d mu. Why? This is nothing but integral over x g chi e d mu, and this is nothing, lambda of e is nothing but t of chi e. So we have found a candidate which works for simple functions. Okay. So now step 2. F in L infinity mu, F non-negative. Then of course F is in LP mu for all 1 less than or equal to p less than infinity. This is because mu is finite. So phi n equals 1 to infinity, simple functions, phi n non-negative, phi n increasing to f. Then we also saw phi n converges to f in LP mu. We have already seen this earlier. Phi n converges to f in LP mu. It was a simple application of the dominated convergence here. Therefore, t of phi n converges to t of f. On the other hand, phi n g converges to fg pointwise. Mod phi n g is less than or equal to f times mod g. Phi n is less than or equal to f. F is non-negative, and this is integrable. Because g is integrable, because we have finite measure, so I forgot to. And integrable, because it's a finite measure. Okay, so therefore g has to be integrable. So I have space here. So phi n g converges to fg pointwise. Mod phi n g is less than or equal to f mod g integrable. Therefore, by dominated convergence theorem, we have integral phi n g over x d mu converges to integral phi g d mu over x. And therefore, and this is nothing but t of phi n, which converges to t of f. Therefore, you have t of f equal to integral over x phi g d mu for every f in L infinity mu. So if f is f non-negative, so if f is in L infinity mu, you write f equals f plus minus f minus, apply the previous result to each of these, and that will imply that Tf equal to integral fg d mu over x for every f in L infinity. So now to prove same is true for every f in Lp mu, and norm t equals norm tg equals norm g p dash. Okay, so this is what we need to prove, which we will do in next time.